Okay, let's just dive right into this. Picture a massive lake. We're talking 1 kilometer long, 40 meters wide, and 10 meters deep. A lake that size holds roughly 400 million liters of water. And honestly, that is the exact volume of blood your heart is going to pump over an average 75-year lifetime. 400 million liters. It's just staggering when you think about it.
Welcome to this explainer. Today, we are taking a journey right into your body's ultimate biological plumbing network. And we're going way beyond standard biology here. We're stepping straight into the fascinating and honestly kind of wild realm of fluid dynamics to really understand the absolute engineering marvel that is your cardiovascular system.
So here is the roadmap for our time together. We're going to start with the evolutionary plumbing problem. Then we'll look at the physics of the pipes, how we actually measure the flow, the recipe for blood itself, and finally, my absolute favorite part, the weird physics of blood.
All right, let's get into part one, the evolutionary plumbing problem. We're going to start with a quote from the source material that really hits the nail on the head. The circulation is an evolutionary consequence of body size. You see, if you're an isolated single cell or microscopic organism, you don't really need a circulatory system. You can just easily get your nutrients and drop off waste through simple diffusion right with your environment. Super easy. But as we evolved into larger, complex multicellular organisms, the physical distances to those deep tissue cells inside us, they became way too vast for simple diffusion to ever work. We literally needed a fast convection system to shuttle materials around.
To solve this, mammals evolved this brilliant dual pump design. On one side, we've got the systemic circulation. Think of this as the high-pressure circuit. It extends from your contracting left ventricle and forcefully blasts oxygen-rich blood out to your entire body. But then, on the other side, we have the pulmonary circulation. This is a specialized, low-pressure circuit driven by the right side of the heart, and its only job is to deliver blood exclusively to your lungs for gas exchange. So you've got two entirely different pumps seamlessly working together in series, perfectly equalizing their outputs.
Which brings us to section 2, the physics of the pipes. Now, the foundational rule we're dealing with here is Ohm's law of hydrodynamics. It simply states that flow equals the pressure difference divided by resistance. And you know what? It's exactly like electrical currents. You can think of the left side of your heart as a constant pressure generator. It creates that initial pressure head, and the resulting blood flow is driven by that exact pressure difference across the varying resistances of all your blood vessels. But let's drill down into that resistance piece for a second using Poiseuille's law. Pay really close attention to the second principle here because it is an absolute game changer. Flow is proportional to the fourth power of the vessel's radius. What does that actually mean for you? It means even a tiny microscopic change in a blood vessel's width dramatically alters your blood flow. If a vessel's radius just doubles, the flow doesn't just double, it increases by a factor of 16. It's wild. Conversely, flow goes down if the blood gets more viscous or thick, or if the vessel's really long. So your body is constantly micromanaging your blood flow just by making these tiny, tiny adjustments to the width of the pipes. Now, as blood actually flows through those pipes, it generally takes one of two forms. Normally, we want what's called laminar flow. This is super organized, it's completely silent, and the blood just glides in these smooth concentric layers, with the very center moving the fastest. But if the blood velocity gets too high, or maybe a vessel gets narrowed from disease, we cross this mathematical threshold known as the Reynolds number. Suddenly, we get turbulent flow. It's chaotic, it's noisy, it literally creates vibrations in your body like a heart murmur, and it wastes a whole lot of kinetic energy. Okay, moving right along to section 3, measuring the flow.
You know, it all comes back to that turbulence we just talked about. When a doctor uses a blood pressure cuff, the fancy term is a sphygmomanometer, they are actually listening for this exact physics in real time. First, they inflate the cuff to completely occlude or block off your brachial artery. Then, as they slowly let the pressure out, a tiny spurt of blood escapes through that squished artery. This creates artificial turbulent flow, and that turbulence produces these sharp tapping noises called choric cough sounds. That very first tap you hear, that's your systolic pressure. Then, as the artery fully opens back up, the flow becomes nice and laminar again, and it goes silent. The exact moment that sound muffles and disappears, that's your diastolic pressure.
Now, if a doctor wants an even more advanced look, they use Doppler echocardiography. Look at those bright reds and blues on the screen. This tech actually works exactly like a police radar gun tracking a speeding car on the highway. Sound frequencies bounce right off your moving red blood cells. If the blood is moving toward the ultrasound wand, it gets color-coded red. If it's flowing away, it's coded blue.
So doctors can visually map out in real time whether your blood is flowing smoothly or if it's getting all chaotic and turbulent as it crosses through a heart valve.
Let's jump into section 4, the recipe for blood.
So what's actually inside those pipes? Well, if you take a tube of whole blood and spin it really fast in a centrifuge, it separates out perfectly into its core components. The top layer, about 55%, is plasma. It's just a pale, watery solution full of electrolytes and proteins. Then, at the very bottom, you've got about 40 to 45% packed red blood cells. This heavy bottom fraction is what we call your hematocrit. And right sandwiched in the middle is this tiny, razor-thin white layer called the buffy coat. It makes up less than 1% of the whole thing, but it packs a serious punch. It holds all your immune-protecting white blood cells and your clot-forming platelets.
Since red blood cells make up such a massive, critical portion of the blood, let's quickly trace their fascinating birth in your bone marrow, a process called erythropoiesis. They start out as stem cells. They mature into pro-erythroblasts. And then, something absolutely remarkable happens. When it reaches the reticulocyte stage, the cell physically ejects its own nucleus. It voluntarily spits out its own DNA. Why? To maximize its internal space so it can pack in as much oxygen-carrying hemoglobin as physically possible before it enters your circulation. Talk about dedication to the job, right?
And finally, section 5, the weird physics of blood.
Okay, to understand why blood is so weird, we first have to define viscosity. Simply put, it's the internal friction, or basically the degree of slipperiness between the layers of a moving fluid. Now, pure water, or even just simple blood plasma, they have a totally constant viscosity. They behave exactly the way Isaac Newton predicted they would. But whole blood? Yeah, whole blood throws Newton's rules right out the window. Think about the difference between a jar of honey and a jar of mayonnaise. Honey is a pure Newtonian fluid. If you hold a spoon of it upside down, gravity alone is enough to make it flow and drip continuously. The viscosity doesn't change. But mayonnaise? It's a non-Newtonian fluid. Hold a glob of mayo upside down and it just sits there, staring at you. It requires a certain threshold of force, what physicists actually call a yield shear stress, before it'll even start to move. And amazingly, whole blood behaves exactly like the mayonnaise. So why on earth does our blood act like mayo? Well, it's primarily because of a specific plasma protein called fibrinogen. When your blood flow drops to low velocities, this fibrinogen causes your red blood cells to actually cluster up and stick together. Because of those clumps, your blood effectively resists flowing. It stubbornly sits there until a high enough pressure, that yield shear stress, is applied by your heart to break up the clusters and force things to move. Once it's moving fast, sure, it acts more like a normal fluid, but at low speeds, it completely resists flow.
Which leads us perfectly to this final thought. Your cardiovascular system isn't just a basic pump with some static garden hoses attached to it. It's an absolute evolutionary masterpiece. We're talking about a dynamic, finely tuned network handling a complex, non-Newtonian fluid that literally defies the laws of simple physics. Every single second of every day, your heart is generating the exact, precise pressure needed to overcome that yield shear stress, perfectly navigating the intricate math of Poiseuille's law across thousands of miles of tiny vessels. So, if your blood is this engineering marvel that defies the laws of simple fluids, how well are you treating your body's plumbing? Thanks for joining me on this explainer, and keep exploring the incredible science inside you.